Welcome everyone to this afternoon's event with Paulo de Souza, Professor Paulo de Souza from the School of Information and Communication Technology. My name is Damien Harris and I'll be hosting the event this evening. But firstly, I would like to begin by acknowledging the traditional custodians of the land on which you're attending from today and pay my respects to their elders past and present, and extend those respects to all Aboriginal and Torres Strait Islanders peoples here today. This event is being recorded and will be put back onto the Impact website, which we'll place in the Q&A bar, so you can go there. It also, if you've registered, we will send you an email tomorrow, and so you can visit that and have a look at anything and share with your friends and family. Also, Impact is a great place to subscribe and find out more about events like this, and also the amazing research that is happening at Griffith University and its impact on society. The format of today is a keynote presentation by Professor Paulo de Souza. During that time, you are welcome to leave questions in the Q&A bar. You'll find that as the little question mark on the side of your screen. Please submit questions anytime during the presentation, and we will do Q&A at the very end. Also, there is a thumbs up icon that you can give to the questions. We will use those to rank the questions, and obviously we'll probably have more questions than we have time to answer. So the ones with the more ranking will be sure to answer first. So before we start, Professor Paulo de Souza is currently, as I mentioned, the head of School of Information and Communication Technology and is a fellow of the Australian Computer Society, with his research interests lying in the areas of microsensing and putting those instruments into unique and wonderful places. And we'll get to that in a little bit. Paulo's undergraduate degree was completed in Brazil, as you'll probably find from his accent, and completed his doctorate at Johannes Gutenberg University in Germany. Previous to Paulo's coming to Griffith University, he worked as a chief research scientist with CSIRO and was quite infamous for his work of attaching tiny little backpacks to honeybees and using those microsensors to track where bees flew and gain very valuable information from the bees with that research. And previous to his position at CSIRO, and the one that we probably will be focusing on most today, Professor Paulo was a scientist for the NASA Jet Propulsion Lab and put some sensors onto several rovers that explored the surface of Mars. And so that's where I'd really like to introduce Professor Paulo de Souza and to discover his 50 years of exploration of Mars and the future of that exploration. Paulo.
Thank you very much, Damien. It's a privilege to be here today and to have a quick conversation with you about Mars and what has happened during the last 50 years and what are we expecting to see in the future. So I hope you will enjoy, fasten your seatbelts. This is going to be a trip to Mars. Now, when we talk about Mars, Mars is a very special place, and why we have so much interest on Mars. There are a number of reasons for that. But if we look at the solar system that we are today, and we think that there are a few places that Mars, that life could be in, and one of those places is definitely Mars. From 50 years before, we sent the flybys, the Mariner, that flew by Mars, took a couple of dozen of pictures from the surface and sent back to us. That's pretty much the image that we would see, and this is an image from Hubble telescope, so it's a beautiful photograph of Mars with the two moons that you can see, those two little bright spots, Deimos and Phobos. And that was it. That's all we know. We looks like there is some ice cape on the north and the south pole. Looks like there is something red, and pretty much the observation on the scientific observation from Mars was not much than just what we see from telescopes. And 500 years ago, if we fast track 10 times further down in the past, we thought that we were at the center of the universe and everything has to turn around us. We were so special and we were created by image and semblance of God. So we were so special. We have to be at the center of the universe. And that homocentrism and geocentrism were so closely linked that when Kepler, Galileo, and others had a look and said, well, actually we are turning around the sun, that was a loss of opportunity, a loss of importance for us human beings, that we are no longer the center of the universe. We are turning around this thing called sun. And that was heartbreaking from us. And if you get yourself in that thinking that we are in the center, why we are not in the center, we are turning around something else. We call that the King Astro Sun, and we live in peace with that existential question for about 200 years, a little bit more, 300 years, when we start looking at the nature of the light being emitted by stars and from our sun, and we saw that was exactly the same. What's going on here? Is our sun just another star, big because it's close by and the other stars are just far away? Yeah, that's the situation. How many stars do we have in the universe? Well, we have more stars in the universe than grains of sand in all beaches of the world. That might give you an idea about scale of the universe and how many stars we have out there, but we are in the only one, the only solar system that is known. And this was pretty much true just by the 80s, literally yesterday, when we identified the first exoplanet, a planet that is turning around a star that is not our star, it's outside of our solar system. Today, and with the mission called Kepler from NASA, we have many other planets, very similar to Earth, and different planets being observed and being detected. We have hundreds of them. Maybe one of them would be a place that we could see life, an intelligent life, like on Earth. Though I doubt we have intelligent life on Earth anyways, Mars looks like to be the right candidate for many reasons, including that we have technology to go to the next planet. We don't have yet technology to go to all the stars and explore the solar systems that we might have seen there. And let's go a little bit back when we see the work done by Schiaparelli in 1877. And that was a scientific interpretation of what we have on Mars. And because of a little bit of a translation from Italian to English, they thought that he was talking about channels instead of canals that were built by Martians. And maybe those lines there would be something that was built by Martians. Anyways, that was already building fascination. And that imagination was filled with that really red dot we have in the sky. Just to show you another example how much impact Mars has on us, we have, this is the cover of the New York Times on Monday, the 31st of October, which is the day after the Halloween of 1938, where Orson Welles was reading a story from Wallace about the invasion of Martians to Earth. This is the War of the Worlds. So what happened at that time? He said, I am going to read a novel. He opened the book and started reading that. But people switched channels later and moved to the radio station where he was reading, and they took that as real. So the cover says radio listeners in panic taking war drama as fact. So they thought the Martians were invading Earth. There was an oh my God at that time, people running to give the last kiss to their families, thinking that the Martians are going to destroy everything. Maybe you remember the latest version of that book became a movie in the 60s and more recently with Tom Cruise about the War of the Worlds. This is a photo of him reading the novel and the famous photo from a farmer in Philadelphia in barricade with a rifle ready to attack the poor Martian that is about to come. This is how much Mars has played up with our imagination. Again, the only observation we had at that time is still through telescopes. Until Mariner, this flyby, Mariner came by and took the first images, close-by images from the surface of Mars. That shows a geography that is dry, there is no plants, there is no cities, there is nothing there. But maybe this was built through a process where water was present, and water is a key element for life. And the strategy used by space agencies like NASA is follow the water. And if you find the water, it's very likely that you're going to find habitable places. Then those images were enough to say, okay, it might worth us going there and trying to see what we have on the surface. And this is where we send then the Vikings, Viking 1 and Viking 2. This is a photo taken in 1976. I was 5 years old at that time. And I remember when that photo was published. The photo shows something that looks like a face. And back there in Brazil as a child, I look at TV live program called Fantastic. It's quite a popular program talking about the face of Christ on the surface of Mars. I could not sleep for a week because of this image. It was again playing with our imagination that maybe there were intelligent life on the surface of Mars. And of course, this fueled a lot of work done by all sorts of mathematicians looking at the face. There was a city nearby with structures that looks like pyramids, and they were in exactly the same ratio of the pyramids in Egypt. You see how much UFO magazines were sold with those images, but still fascinating to see how much we are compelled to see that there was an intelligent life there. Before I move on, I just have to say those are just shadow and light reflexes on mountains. There is nothing like a face, a real face that was built by Martians on the surface of Mars. So Viking landed, and this is one of the photographs taken there. And the analysis through the spectrometers in that lander showed us that this place was dry. Was so dry that never ever saw water. This is solidified lava, is what we call made of primary minerals, minerals that would have transformed into weathered into something different if they have seen water. So it was a big desolation to see that. I remember colleagues that work with one of the principal investigators of that mission, Carl Sagan, saying how disappointed he was because of the absence of a bush or a little green Martian waving to the cameras or anything like that. We forget it. So what happened then in 1984? I will jump into a few years. An expedition of NASA went to Antarctica and found a crucial piece of rock that is a meteorite. That meteorite is called ALH 84001. Allen Hills 84 is the year that was discovered. 001 was the most important rock at that. And you see a cube of 1 centimeter there. So you have an idea, it's a pretty small piece of rock. That rock came from Mars. And we know that because the analysis of radioisotopes made by Viking show us that they are in the same ratio of the radioisotopes in this meteorite. Different from meteorites that came from the moon, and we can analyze moon rocks and see there are different ratios of radioisotopes from Earth and from other minerals, from other meteorites. Those meteorites are called SNC, meteorites that came from Mars. What happened? A big meteorite hit the surface of Mars and ejected pieces of rocks to space. They were big enough to be captured by our gravity, go through the atmosphere and hit the ground. That one was discovered in Antarctica, which is a beautiful place to find meteorites because the ice moved towards the mountain, and then you can just walk by the mountain valleys and you will find them, a lot of them. That meteorite is from Mars. The DNA analysis of a rock tells us it's from Mars. But more than that, it is made of carbonate. Carbonate is a mineral or a group of minerals that needs water to be formed. So a rock from Mars that was formed into a wet environment. And if that was not enough, there was a little structure that you might be able to see that looks like a little cord. It is a solidified or fossilized bacteria. That's the interpretation. And inside that, you will have a string of magnetite. Magnetite that is exactly the same we find in bacteria on Earth called Aquaspirillum magnetotaticum that use the magnetic field to orient itself. Now, it's still controversial if that is a bacteria fossilized, if that is a string that necessarily was formed through life. It could be formed through other processes that are not necessarily in need of life. But anyways, that was a discovery that might be our first evidence of life beyond Earth. And that was a information that was released by a press conference by the American President Bill Clinton at that time, not only to announce the discovery that was considered very important, but also to tell us that maybe Mars was habitable and we should go back. So that was the discovery of water on Mars, literally. It's an indirect evidence. And this is why NASA came back in 1997 with the Sojourner, with the small rover from the mission called Pathfinder, that navigated 104 kilometers around the lander, analyzed rocks, and those rocks are exactly the same rocks that were found by Vikings. What's going on here? Do we have real water on Mars? Why these minerals that we analyze from those landers will never find something, landers and rovers could not find any evidence of water there? Probably we landed in wrong spots. And this is where then NASA sent missions to orbiters to take better photographs from the surface of Mars and then select places to land. And out of 174 potential places to land, we came down to 4 and then finally with 2 that I have the privilege to be one of the participating scientists in with the Mars Exploration Rover. That is a much bigger rover, and I will show you a comparison of size from Sojourner to the Spirit Opportunity. In this photograph, you can see in the first plane here Spirit being tested in the clean room at JPL, and back there you see Opportunity without the wheels, is still to be built. So those are the twins that we sent there. My work was as part of a team in Germany that developed one of the sensors that was used to analyze characterized minerals on the surface of Mars. This is an image taken from that rover already on the surface of Mars, and you can see that little box pointing towards us, just in between the wheels in the robotic arm, and that is the one that I helped to develop, this one here. It's a spectrometer. Let me show you a couple of images to tell how important is the infrastructure around those missions. It's not just about having a lander doing things, it's about also having orbiters around. And orbiters not only from NASA, we have a great mission from the Indian Space Agency with an orbiter. We have also the European Space Agency with Mars Express and with ExoMars, also getting more information and also being the communication channel. The data sent sometimes directly from the rover to us, to Earth, using a small dish that is in the back of the rover, this little dish that you might be able to see here. So this is DT, direct to Earth, or you can use a big stick that is on the back of the rover that is a low gain antenna that you can talk to satellites, which is much less energy intensive. So you save a lot of batteries. So after we landed, you can see in the top left of the image, you can see the back shell and the parachute of the rover. You can see the tracks and where the rover was around the crater we call Bonneville. And this is where the heat shield is a part that protects at the entry of the atmosphere has impacted. So it is 2 pieces. One is a parachute and back shell. The other one is the heat shield. They open inside. You have airbags that bounce on the surface, and this is how you land. And then you have the tracks, and you can see that from space. I will show you an image soon about seeing that from the surface. Also on the bottom, you can see the lander. So let's start from the lander, how that looks like from the surface. This is an image taken from approximately 400 kilometers from the surface with a satellite. And this is an image taken on the surface by Spirit looking back to where we landed. So this is called Columbia Memorial Station, that was named after the Columbia crew. I will just move again to to show you the heat shield back again. Lander tracks where we went to craters. Craters are a great place. I'm going to talk briefly about it. And then you have the heat shield impact where it crashed on the surface. So this is a Bonneville crater, and you can see the heat shield amplified a little bit on the top. So you can see a little bit bigger there. This was an interesting place to have a look. So you can see how much temperature on the surface of Mars changes. Mars is a fascinating place. It is pretty cold. In a very hot day, I would say the temperature will be close to 0 degrees, a little bit warmer. Maybe it has to be really, really warm. If we have Martians there, they will go to the beach. If we have a beach and an ocean, because it's going to be really very hot. But every night it goes to temperatures below -80, -100 degrees in Celsius. So this is how it looks like at 10:15 a.m. Imagine that you have special glasses and you can see in color temperature. If it's red or close to red, like orange, yellow, like you would see on the left side a little bit, this is close to 0 degrees. In shadow, you would have -50. So it's pretty cold. 10:15. 11:45, it's warming up, so it's much warmer. 1:30, 2:30 starts getting cold again. Now between 2:30 and 4:30, the temperature drops 50 degrees. So you see approximately in the base of the crater, approximately 0 degrees, and then in 2 hours, the temperature drops to -50. Your instrument must survive that temperature changes every day. So anything you send to Mars has to go through that thermal cycle every day. All the electronics, everything has to be put to survive stresses like that, just the temperature stresses, cosmic radiation, and many other things. Gravity on Mars is about 38% of ours. The atmosphere is quite thin. We thought it was probably much warmer, and I will tell a little bit about it, but it gives you an idea on how we are in terms of temperature today. And the atmosphere is just 1% of the atmosphere we have here. Winds can have really be very, very intense. So you have dust storms that takes the entire planet at once. And they can last for several weeks, if not months. And when that happens, we cover the solar panels with dust. So it takes a lot on the rovers. We can't communicate if the storm is too dense. And the wind can get up to 400 kilometers an hour. But why that doesn't fly the rover away? Because the air is quite thin, so the pressure is quite small. The pressure is like a breeze. You won't probably feel it, but the particles will be jetting the rover at that speed, damaging the structures for sure. Now, if you want to have fun a little bit on Mars, we can make a little bit of calculations. So have an idea. The day on Mars is a little bit longer than the day here. We call it Sol, just to not be confused. So this is the first curiosity about Mars. So it spins around itself a day, 24 hours and approximately 40 minutes. So if we work with a rover on the surface of Mars, it has to wake up the rover every day, let's say 9 a.m. in the morning. Tomorrow will be 9:40, then 10:20, then 11 o'clock, then 11:40, then 20 past, 1 p.m. So it's like a daylight savings every day. It's terrible on you. So you know how it feels to have just 1 hour. Imagine that 40 minutes every day. So it's quite challenging to work. The other thing is that the Martian year, to take around Earth, it takes approximately 26 months, terrestrial months. So I am 49 years old. So if you would like to know your age on Mars, multiply your age by 12, number of months on Earth, and divide by 26, you'll have an idea. So if somebody asks my age, I say I'm 22. If I were on Mars, so I'm not 49 years old. So age is relative as well, so you can say that way. Now, the worst thing you can ask a Martian scientist, it's something like, call me on Sunday, 8th of December, 5 p.m. That is terrible because I have to calculate 40 minutes late on Sunday what's going to be the time. It's just not going to happen easily. So it is very difficult. We usually use some watches that gives us the Martian time. But to do that, you have to do a little bit of calculation to know if you are able to give a phone call 5 p.m. So it's one of the challenges there. The distance is another one. It's far away from Earth. So any information to travel to Mars to reach the rovers will take approximately 20 minutes. So if you take the phone and say, hello, traveling at the speed of light would take 20 minutes to get there. The rover will hear hello, and then he will say hi. You have to wait additional 20 minutes. So you say hello and wait. So if you have to drive the rover on the surface of Mars, you turn right. You have to wait 40 minutes to know if the rover actually did it. So it's impossible to drive the rover that way. So the rover has to be, in many ways, or any machines we send to Mars, it has to be a robot. It has to be fully autonomous to a point that we can say, go to that rock, and the rover has to find its own way to get there. And the only way to get there is analyzing images and building hazard maps and trying to find a way to get there. So it's really difficult. And we never say, yesterday on Mars, we always say yes to Sol. So that's a little bit of curiosity about the day and the Sol. Sol is a day on Mars. So this is how we say it. So this is with curiosity, with Opportunity, with the second rover. So that is the lander, and literally it was a hole-in-one. So the rover came bouncing, bing, 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 and then it rolled inside a little crater called Eagle. And this is a little bit of a selfie, if you prefer. The rover took of itself. You can see this stick coming up, this bar, which is the low gain antenna that I made a reference to. There's a little bit of a calibration target for the cameras sitting right here. It also helps us to see colors and calibrate the camera, plus the sun, time. And there are a few words written around, which is the word Mars in many languages. But that gives you the solar panels, and you can see a little bit of the landscape. I'm going to show you what we have done at that spot during 3 months of the mission, which is the primary mission. So we analyzed the ground ahead of us. If we are looking for weathering evidences, we probably won't look at the soil, because the soil is quite homogeneous around Mars. All these dust storms make it quite the same everywhere in the planet. So the best thing to do is to dig a little bit, analyze the subsoil, or analyze rocks. We have a polisher that polishes rock. You see some holes there, and then we can expose the fresh rock. And by analyzing the surface and the fresh rock, you know what kind of weathering transformed that rock into new minerals. This place was a gold pot. We had so many interesting discoveries done. This is where we found the first evidences that Mars was once wet, and it was a lot of water. The question at that time, right at the beginning of the mission, for how long the water was there? There was clear evidences through the minerals. So the minerals were jarosite and hematite. It needs a lot of water to be formed. There's no question about it. This is a little meteorite that we found there. It's called bounced rock, which is actually a meteorite, similar to the one that we found back here on Earth. But for how long that was there? So to answer that question, we need to move to craters. Craters will give us that whole profile of meters and meters of geological story there for us to analyze. So let's just move a little bit to the next, so that will give us an idea of some of the discoveries done at that spot. So we found blueberries on Mars. Blueberries are the nicknames we give for these little spheres that are blue. You can see plenty of them on top of this slide here on the top right. You can see those little blue pots. It looks like blueberries. And you can see the layers of deposits that has been formed here, partially eroded by wind, but also the presence of that. There's a beautiful paper that I co-authored about the genesis of this place that tells a lot about evaporitic processes where the water was present and then it evaporates, leaving behind. We have similar structures like this on Earth, particularly in the outback. But they are rich in magnesium. These ones are rich in hematite, iron oxide. There's only one way for you to form that, is with water and water in movement like an ocean bed. So I'm just going to have a little bit of fun here. So we have Victoria Crater. This crater, it's about the size of a stadium. That gives you a sense of scale. There is a little scale here down that gives about 500 meters wide crater. Eroded, you can see that there was a lot of erosion, a lot of sand dunes on the bottom building up. And there is a yellow, I hope you can see a little yellow lane here that goes there and then comes back. Those were places we visit with opportunity. And there is a little dark spot right in this place. Maybe you can see a little bit dark with the blue text written. So this little blue point here, if you were here and you look towards that direction, you would see a big wall in front of you and some structures of the crater. So this image was taken from a high-rise sensor sitting on 500 kilometers from the surface, looking down where opportunity was. And if you were there, you will see a big wall and structures of the crater. This is the big wall and structures of the crater. On the back, you can see a little bit of the sand dunes. So this is the image taken by opportunity sitting right here. So this photo was taken from space, orbiting, and then you have another one taken by opportunity at that spot here. How thick is this? It's about 8 meters thick deposits. You can see the layers of deposit forming at that spot. It's pure hematite. You need water for a long period of time to form that thick deposit. This place was an ocean bed, and this ocean was there probably for millions of years. The question now is different for scientists. Is this water enough to form, let's say, was there to form life? And if life was formed, was able to evolve in that process? Where all this water went to? So the answer for that question, that is a little bit of a point that every scientist would agree, is that the magnetic field of Mars cooled down. And in that process, it lost its magnetic field. So the core cooled down, the magnetic field is gone, so we don't have the magnetosphere, what protects the planet against the solar storms. So the planet lost that protection, and then the solar storms came and washed away the atmosphere. As you decrease the atmosphere pressure, you evaporate more water. As you evaporate more water, another storm comes and takes that away, and keep that process for billions of years until you have a dry planet. Part of that water was kept into the capes, which is mostly made of CO2. But you do have water preserved in salty water on the south of that. And there was an announcement done recently about the discovery of liquid water on the south pole of Mars. That's a wonderful place. And I'll show you us leaving the crater. You can see the dunes down there, the wall that I showed, and us leaving the tracks behind. We're driving backwards at this point for a number of reasons with opportunity, including that one of the wheels could have got jammed. Now let me show you, we have two moons on Mars. I said that right at the beginning, Deimos and Phobos. So this is Phobos egress. So we are seeing the moon rise on the surface of Mars with the rover. We have the moon, we have the sun, we might have eclipses. So this is the sun and Deimos passing in front. So we recorded an eclipse on the surface of Mars. It passes only once. I'm just showing here, repeating the video. It's not that fast, but you can see an eclipse on the surface of Mars. You could also see us. This is Earth seen from the surface of Mars. It's fascinating. I remember when we got this photo and looked back, that tiny blue spot that looks, if you are in Australia today, you look to east. By 8 p.m., about 30 degrees in the sky, you would see a red dot, that's Mars. And if you were on Mars, you would see Earth twice as big as that, because we are twice as big as Mars. So you would see that. There's a very popular program here in Australia called Sunrise. There is another one that is very popular on Mars called Earthrise. And this is Earth in the sky just going up. As you see that. It's fascinating to look back and see how important we are. We are the center of the universe. Everything has to turn around us. And that is, we are the only place with life in the universe. Now, serendipity and science, they work together. I'm showing you the wheels of a rover that is jammed. I can move that wheel, the right wheel. The left wheel is in the sand. There you can see the wheel literally disappeared trying to get moving. We have 6 wheels in this rover, but the right one was jammed. We couldn't move that. And because of that, just by chance, we trenched the soil whenever we go, and we found some bright things there. And these bright things, we came back, we thought that were salt, and actually it was silica, pure silica. And that was probably one of the most important discoveries we did in this mission. This pure silica to be formed, which is opal, it's the same rock of Australia, it's opal, the same we have in South Australia. It has to be formed into hydrothermal system, so it's hot water, bubbling water there that would form this silica. And wherever you have water, energy, nutrients, you have the perfect ingredients for life. So this place would be a candidate to have fossils, for example, of bacteria that could have been formed at that time. And just by chance, and this is the paper that we published in Science, one of those but this one was talking about the detection of silica-rich deposits that we found is opaline, so opal that we found on Mars with Spirit. Now, talking a little bit about what we have today, this is a photo that gives you a little bit of context. You see the little piece of Sojourner, which is about the size of a microwave oven. You see Spirit Opportunity, the size there, behind the back of one of the engineers there. And you have Curiosity. So one is about the microwave size, the other one is about the size of a golf cart, and the other one is about the size of a minivan. The way we land with them, it has to be completely different. Sojourner and Spirit and Opportunity was landed with airbags, while the Opportunity has to be landed with cranes and a very complex landing because of the weight. You won't comport that properly with airbags. But that gives you a sense of scale, and a lot of things has to evolve. Not only it's not about making it big, but also make it safer to land on Mars, which is very challenging. So what we would expect in the future, in the immediate future, what we have, as we have today, 3 missions going to Mars. The first one is Tianwen-1 from China. This mission is quite ambitious, and for a number of reasons. Most of all, it's an engineering challenge. They have not only an orbiter or a lander like Vikings, or other missions that try to do that, like the one that I have one instrument on board as well that we, as a team, we built. It was Beagle 2 from Mars Express that failed in the land. It is complex, but also they have a hover that is sitting on top of that lander. So you have the lander, you have the hover, and you have an orbiter. So it's quite ambitious mission, and I would say that if successful, and I hope it will be quite an accomplishment of engineering that we have today. The next one is Hope from the United Arab Emirates, a wonderful visionary mission looking to build a comprehensive atmospheric observation and understand the atmosphere of Mars better than we have done before. I really praise the United Emirates for the work they have done to put a mission at this level of complexity together. I know there are a lot of collaborations going with MPAG, with NASA supporting that mission. But this is what a great vision from that country to say we will do this and we're going to send a spacecraft to Mars, just like the Indians did successfully as well. This is fantastic. So it's great to see that much effort. And the other rover is Perseverance. It looks very similar to the Curiosity, the rover that I showed you a photo with the engineers. You might have noticed that there is no solar panels there. There is an internal battery that takes care of the energy of the rover. But that rover has something interesting. It has a helicopter that's called Ingenuity. The helicopter will be sitting below the deck. It will just be laid, and then the rover will move away, and then that will be an assisted robotic mission, flying in and coming back, going out and back all the time. And one of the targets, or let's say the objectives of this mission, is to select samples to send back to Earth by 2031 with the sample return mission. So what we expect to do is to find interesting rocks. There is a lot of meteorites on the surface of Mars. We don't want to take meteorites and put inside a rock and send back, because it's not going to be a rock from Mars. It will be from Mars, but not originally from Mars. It would be interesting to bring a rock that actually was from Earth, a meteorite from Earth on the surface of Mars, and bring it back. So you need to characterize those samples really well and say this is a sample. For example, from our previous mission, I would bring some of this opal if we had a chance to find something like that. Put that inside a capsule that another rover will come, take it, put inside a rocket and ship that back to Earth. And then we will have to collect that and bring that down to Earth, and then use instruments that cannot be miniaturized, like particle accelerators, to have a comprehensive, complete, as accurate as possible chemical analysis of rocks that will tell us a lot about them, or powerful microscopes that we can't have on the surface of a rover, that we will be able to use them back here on Earth and advance our knowledge about it. And all that will lead to, of course, the preparation for eventual manned mission. So we will have astronauts going to the surface of Mars. Why we do this? For many reasons. The first one is back to that question that was with us 500 years ago. Are we alone in the universe? Are we the only one planet with life? Where we came from? So if we stop and think about this, it's dealing fundamentally with reasons for us to consider why we exist, and if we are alone in the universe, and fascinating. The other one is, of course, Earth is not going to be here forever. Our magnetic field is not going to be strong enough to protect us from our sun, and that could be the end of the human race forever. So if we are here to survive as a species, we need to find other places where our next generations will be able to move to and to live at, and continue the endeavor of what it looks like to be a race that is able to explore the universe, just like the sailors did before. Finally, in that direction, and I hope we will be able to bring the benefits of the technological development of things that we develop for space back to help us to have a better life right now here on Earth. And probably one of the most pragmatic views that we have from all countries that I have been exposed to when it comes to space research and space industry is in Australia. So the vision that Australians have about bringing that benefit to create jobs right now, it's so clear from the baby that we would say is the Australian Space Agency. It was created with that strong view to create jobs for the future, to create opportunities for our industry to be part of this endeavor of exploring space. And I think that is what we need. We need to have that vision that whatever we do, that we bring new generations of explorers to build this. And I hope there will be a lot of kids listening to this talk, because this is the future for you to build. It's for you to realize that. It's for you to continue that journey. That is part of our DNA, is to explore. Otherwise, we will stay in caves somewhere and not exploring Earth and exploring our solar system. And in terms of technology, we're still doing nothing. This is fascinating in many ways, but it's boring in many other ways. We can only go to the next planet. We cannot even go to the next grain of sand, which will be the next star. We don't have yet technology for that interstellar trip. But I hope one day we will have, and then we will be able to explore to the extent of the universe that we can. So with that, I would like to thank you so much for your attention, and I'm going to move then to questions and answers. Thank you.
Thank you, Paulo. Thank you, Paulo, for that fascinating presentation. We are having a few questions coming through. Firstly, from Shauna, sorry, I've got a puppy in here as well, one of the working at home casualties. Professor Paulo, does self-driving on a rover use the same principles of AI principles as self-driving cars like a Tesla?
Probably in some ways, yes, it uses images. It's part of that. So you have cameras looking. It is pretty slow. When you think that there is, like on Mars rover, a quite advanced controller or microchip that is able to make a lot of calculations in a short period of time. No, it's not what's happening. In space, we need to have things that work. They are reliable. So it's old microcontrollers, old microchips, old computers, if you prefer, that can analyze just a small amount of images and process and then move a little bit, process again and move a little bit. But the principle is the same in many ways.
Thank you. The next one from Maggie Mermans. I have a question regarding space litter. With all the space missions, I'm wondering what organisations or countries are doing in order to clean up, mitigate the issues of littering, and if this is taken into account when building, engineering, constructing all the amazing equipment that goes up there. And secondly, what are the issues with space litter, if any?
Yeah. First of all, yes, there is a lot of, and Australia is the one that is doing a lot in terms of tracking objects in space. Just last week, the International Space Station has to move up its orbit to get on the way, out of the way of a junk that was flying from a Japanese, nothing against Japanese, please, it's just that was a Japanese rocket that was a piece of that rocket that was right on the way of the International Space Station. So this is happening all the time. So we need to keep tracking where they are, where they're flying to. So that was the first question. The second one, there are a number of challenges. The more things we send to space and the more access we have to space, the more junk we have out there, the more risky it will be for us to send new missions there. You might send a rocket that will hit a piece of another old rocket or a piece of a satellite or something else. So we need to start looking at ways that we can not only do better tracking to avoid that to happen, but also to clean up. That is really needed.
Thank you for that one. Another question on, are we looking at mining Mars? And if we are not successful in colonizing Mars?
Yeah, I think the richest mineral we would find on Mars would be water. So if we can use the water, and we need to use the water to produce a lot of things, that would be the one. Not that we want to bring things from Mars back to Earth and make use of that. The minerals we have there won't be really profitable that way. If I have to bring something from space to make something that will have material value, would be asteroids, especially metallic asteroids that will have a lot of iron and nickel. Otherwise, it will be boring. But if we have something like a diamond, we need to have carbon. We have to have carbon from life as well. So there we go. Oil, definitely we won't have on Mars because we will have dinosaurs and plants and everything that over pressure would form that. So in terms of minerals, no, this is not the reason why we go. The only thing we can definitely use a lot would be the water. Maybe there will be a few other things there, like titanium, maybe a little bit of iron, but it will be very hard to produce anything.
And the next one, hold on. Professor Paulo, as you mentioned, Earth is not going to last forever as the sun is going to become a dwarf star. So do you believe our technology is ready for a Proxima Centauri or Alpha Centauri? Where do we stand at that point, ignoring the problem with propulsion technologies we have at the moment?
Yeah, we're still a long way to find a way to travel to another star. It has to happen, otherwise the Homo sapiens will go forever. So the only way for us to exist as a race, but don't worry about this. It's going to take a few billion years to happen. So we have time, but the journey starts with one step, and this is what literally we're doing. We have to develop the technology. We're still very, very premature in terms of technology development to do something like traveling to the next star.
Since I'm moderating, I'm going to throw in one of my own questions. Paulo, are you currently under research or looking at doing any research on future sensors or space technologies?
Yeah, of course. Here at Griffith, we will develop. We're establishing a space technologies lab. So that will be right here at the Gold Coast, giving a chance for students at Gold Coast to have fun in developing technologies to space. We do have a couple of sensors aligned to some missions. Most of them will be satellite, that we will have a chance to understand better the weather in space and do very cool science right here. Absolutely. There will be more announcements coming soon about it. Can't tell much.
One of the last ones, in the near future, what AI advancements are we looking for that will impact the exploration of Mars?
Ooh, there will be so much. AI has the ability to, of course, substitute the man in many things. The human being is not necessarily has to be there for a machine to operate. And most of those machines, including the rovers that we have today, they are interactive in the way we work with them. So we give them a task, they realize the task, send the results, we analyze and say, let's move to the next point. Oh, this looks so good. Let's stay here a bit longer because we found blueberries. And so we stayed there for several weeks because that was really a beautiful place that we were looking for. Why the rover is not able to do that by itself? Why we still rely on that much? It's part of the strategy. Of course, it's a very expensive mission to do something like that, and you want to have some level of control. But ideally, we should give more autonomy to the rover, and that will only happen if it's able to bring some rationale around the hypothesis of what they are trying to solve. I will try to find these type of minerals, and let it go. Let it try to find it, and the rover will try to find itself. So that will rely a lot on artificial intelligence. The more images we collect as well, images are very heavy in terms of data, transmission of data, so probably we don't need all the images where we collected, but you can have some pre-processing of that on board of the rover using artificial intelligence as well, finding patterns, finding interesting things, and making discoveries while you are on the surface of the planet, instead of sending that back for us to have a look.
Another question has just come through. What are the different, you mentioned it very briefly, what are some of the different ways or methods used to land the rovers on Mars, and what are some of the future advancements?
Oh, that's a very interesting one. Let me show, I have a video ready to go here. Let's see if I can play that. So you can see a comparison between Mars exploration rover Curiosity, which will be very similar to Perseverance a few months down the track. So in approximately 5 months, we will land on the surface of Mars with something that looks like the second video. I'm showing you first the landing with Spiritual Opportunity. So I hope you will be able to see this. I will now play. This is what we call EDL, entry, descent, landing. So we separate the cruise stage, and the way we start braking on reducing the speed is through friction with the atmosphere. It's very thin, but still you have that effect, reducing the speed. When we are traveling about 1,200 kilometers an hour, you open a parachute. It's faster than any jet flying. But remember that the atmosphere is not that thick, so you're still okay. But you are reducing the acceleration, and of course you're braking, you're reducing the speed further. Remember that heat shield, that was a bullet view that just being released. You have a little package. You have the back shell, parachute, and the package. And then when it's close to the surface, it will inflate the airbags. Cut a wire. You have a retrojets that goes stop, stop, stop. Cut the wire, let it bounce on the surface. Take the parachute away from the hover. So this is where you saw parachute and hover away from the lander. You saw the heat shield close to Bonneville crater. And then we bounced 32 times with Spirit on the surface of Mars. The center of mass is dislocated, so it's not right at the center of that pyramid. So whenever it stops, like that toy that you touch and it bounces back and stays standing. So it stands like that. In approximately half an hour, it deflates the airbags and opens just like a flower with 6 petals. 3 are solid and 3 are flexible. And we land through the ones that are flexible. This is how we go down. And inside that, you have the rover. It will open the solar panels. We have cameras below the deck, we call HAZ cams. We took some images with the HAZ cams, start sending data through the low gain antenna, that is still up, to satellites orbiting. We raised the neck of the rover that has also a number of instruments, the thermal emission spectrometers and color cameras that take panorama cameras that take photos. And then we open the little dish. We look around, open the eyes, and start taking images of the surface of Mars and send that back to Earth. This is pretty much the end of the entry, descent, landing of one of the rovers. So I'll show you quickly the other one. Do we have time still?
Yes, yep, we're good.
Okay, we'll take just 1 minute to show that one. So this is Mars Science Lab, which has the rover called Curiosity. Let me share my screen and you will be able to see it, I hope. So just bear with me. I think you might be able to see Mars. And then this spacecraft is much bigger. To stabilize that, you have to have jets on the back that will make it stable as it enters the atmosphere. You can see that. It will also open a parachute. This rover weighs about 1 ton here on Earth. Our gravity on Mars is 38% of our gravity here. So you open the parachute, still coming down, release the heat shield that protected the rover from the entry of the atmosphere, and then you release a little spacecraft that actually is going to be flying around with retrojets going down slowly. The rover is attached to that structure. It has some, it works like a crane going down with the cables. When it touches the surface, it cuts the wire and will take that structure with the retrojets away. So you have a very gentle landing on the surface. Cut the wires, fly away, otherwise you will land on top of the rover and you won't be able to move anymore. So this is how the second landing worked. So to give you a little bit of a flavor of different ways of how we can land. So answering that question. So with the first one, we landed with airbags, like with Sojourner, with Spirit, Opportunity. This one's probably too heavy for you to do that landing, so you have to have a completely different way of landing with rovers on Mars, if they are that big. Again, with the Chinese mission, will be a lander that will land, and then on top of the lander, you have a rover that will go through a platform and reach the surface.
I think we have one last question, and it's quite similar to one that was before, but I think it has a little bit of a different angle. What sort of technologies do you think will be required to make a sustainable colony on Mars?
Oh, definitely, there's so much to be done. And this is an area where doesn't matter what you, let's say, if you are students out there, what you want to study, there will be a place for you in the space industry. If you want to be a doctor, how all the aspects of the absence of gravity on the trip to Mars, or even a psychologist looking at how can you be with a team for that confined space for that long on a place like in a spaceship going to the surface of Mars. How is your body going to react when it gets again back into gravity, 38% of what we have here? All those aspects or human aspects will need to be present, and we still have to evolve a lot. We have at Griffith, for example, a professor in physiotherapy that is studying astronauts when they return to see how the spine reacts to the time they have been in space, and understanding how eventually injuries could be settled or could be prevented in that way. Having a habitat that is a place that will be habitable for you, how to extract water and reuse the water properly, how to grow plants. It's simple for you to say, just put a seed inside the habitat. The soil there is so acidic. You have so much sulfur. It is not the proper soil. It doesn't have bacteria in as we have today. That's what we believe. So it's not really a fertile ground. So many challenges. I keep going, talking about all of them. The key message, I think, is if you are a student, it doesn't matter what you do from medicine, psychology, engineering, physics, chemistry, mathematics, communications, like Damien, you will be able to you will have a place in the industry, in space industry for sure.
We've got one last one that just came in.
Yep.
Thank you for the talk, Paulo. In navigation, do you have a set of external reference points, or are you continuously recalculating and setting new internal reference points? I know how difficult it is for autonomous vehicles to navigate in the snow.
Yeah.
Mario.
Yay, that's good. Look, we do have star trackers. So we look at stars. And by looking at stars, we know how they should look like. So if I am looking at stars on my little screen, which is the sensor, star tracker, and I know how they should look like where I am, if that star changes, it's because I'm pointing to the wrong direction, so I should go back and move back and keep tracking in that way. So this is an important part of the navigation. We use exactly the same way we used to navigate when we traveled the oceans, or when the Aboriginal people were going across the outback by looking at stars, and they have an idea where they have to go. It is the same way. There's nothing different. So we use the star trackers to help us to go to the right place by looking at the right stars at the right time.
And I think that's a very positive way to end. It's almost like the history of what we used to do is come back to how we navigate on Mars. Thank you, Professor Paulo. That was very informative. I hope you all enjoyed the presentation. I would remind everyone that this presentation will be available on the Griffith Sciences Impact site tomorrow morning. And please feel free to subscribe to that site to get your first invites to events such as this and across all the disciplines that we have here. Our next event is on the 15th of October. It is on the future of STEM careers. It has a panel of different industry members from all across different STEM disciplines, and we're very excited to have included the Queensland Chief Scientist, Professor Hugh Possingham, on that panel. So it should be a very interesting discussion of how the world is rapidly adapting in response to the public health pandemic, the effects of globalisation, and how these reforms are changing the needs for professionals in STEM industries. I hope you can make it along to that event. That is all for this evening. Thank you everyone for your questions. Thank you, Professor Paulo de Souza. Good luck with your next missions, whatever they may be. And until then, we wish you well and hope to see you at our next event.
Thank you. Bye-bye.